Good morning, students. Welcome to the next lecture of electronic measurements and instrumentation. In this class, we will see harmonic distortion analysis. My name is TSS Nagpavan Kumar. So, let us see the concept of harmonic distortion analyzer. First, see what is meant by distortion analyzer. Then we will see harmonic distortion analysis. So, distortion analysis. The extent to distortion analyzer. The extent to which the output waveform, see here, the output waveform of an amplifier differs from the waveform at the input, when the waveform at the input is a measure of the distortion introduced by the inherent non-linear characteristics of active devices such as bipolar or field effect transistors or by passive circuit components. Okay, so see here the distortions which are differing from output to input, those parameters we are measuring with the help of amplifier, with in an amplifier circuit which is consisting of BJT transistors or field effect transistors or maybe any other type of passive components. Let us see once again the extent to which the output waveform of an amplifier differs from the waveform at the input, when the input is a measure of distortion, right? How much information is differing from output to input, that is called distortion, is introduced by the inherent non-linear characteristics of active devices. Whatever the non-linear characteristics are available through the active devices, such as bipolar or field effect transistor, that is bipolar junction transistors or field effect transistors, are by passive circuit components, So this is about distortions. The amount of distortion can be measured with a distortion analyzer. The amount of this distortion we are measuring by using a distortion analyzer. Let us, all the signals have some of the harmonics. These harmonic distortions here we are going to measure. These distortions in the form of harmonics we are going to measure in this harmonic distortion analyzer. Okay, let us see the harmonic distortion analyzer. In the harmonic distortion analyzer, the first one, fundamental suppression type of distortion analyzer, now we will see. A distortion analyzer measures the total harmonic power present in the test wave rather than the distortion caused by each component. Here, in an amplifier, lot of components are available to create these harmonic distortions. But here, we are not taking the distortion caused by each component. The distortion caused by all the components, that is, we are taking the total harmonic distortions, the total circuit harmonic distortions. A distortion analyzer measures the total harmonic power, present in the test wave rather than the distortion caused by the component. Each components. Now we are measuring all the components distortions. We are measuring the total harmonic power. We are measuring by using this harmonic distortion analysis. The simplest method is to suppress. The fundamental frequency by means of a high pass filter whose cutoff frequency is a little above the fundamental frequency, right? So, the simplest method to suppress the fundamental frequency by means of a high pass filter, right? We are using a high pass filter whose cutoff frequency is little bit above the fundamental frequency. So, this is the simplest method we are using for measuring the total harmonic power. This high pass filter allows only harmonics to pass and the total harmonic distortions can be measured. So generally, what is the high pass filter operation? The high pass filter operation which allows the high frequency selected components, and it is not allowing the low frequency signal components. So the high frequency signal components which has the magnitude information, that is the total power information, that information is allowing that harmonics power only we are allowing, we are passing, and we are measuring that harmonic power. We are measuring that harmonic powers. So that is a major concept behind under this fundamental suppression type. Other types of harmonic distortion analysis based on the fundamental suppressions are some of the concepts we will see. So three variety of concepts now we will see, and they are based on this fundamental suppression type. Based on this fundamental suppression type, we will see three variety concepts of harmonic distortion analysis. So in that, the first one, the harmonic distortion analyzer, the first one, employing a resonance bridge. Okay, in that wave analysis, we are employing this employing a resonance bridge. So in this resonance bridge, see here, so this bridge consisting of totally 4 arms. In the 4 arms, we have one side R1, second side R3, and third side R2, and last side we have LC components R1, R2, R3, and LC components. And two leads of this bridge, for example, see here A. Here we have A lead and B lead. So in between A and B terminals, we are connecting to the test wave, and the remaining two terminals, this is C and D. In between C and D, we are connected a harmonic detector. We are connected a harmonic detector. Whatever the harmonics, the total power we are measuring by using this harmonic detection by using C and D terminals. In between C and D terminals, we are measuring the harmonic power. This is the basic resonance bridge. Okay, let us see the discussion of this employing a resonance bridge. Okay, the bridge is balanced for the fundamental frequency. So whatever the bridge now, just now we have seen, the bridge is balanced at the fundamental frequency. That is, L and C are tuned to the fundamental frequency. So the bridge is balanced with the fundamental frequency. That is okay. But what about that fundamental frequency? How this bridge is tuned to the fundamental frequency? In the fourth R, we have L and C components. In the fourth R, we have L and C components. With the L and C components, we are tuning to the fundamental frequency. The bridge is unbalanced for the harmonics. That is, only harmonic power will be available at the output terminal and can be measured. So actually, whenever the harmonics will be present, at that time bridge is not going to be balanced. At that time, whatever the differences will be there, that harmonic magnitudes or amplitude information will be measured with at the harmonic meters, right? At the point of harmonic measuring devices. Okay, but for the remaining combinations, the bridge is going to be balanced. With this, we can measure only harmonics behavior. With the help of this one, we can measure only harmonics. We can measure harmonics at the output terminals. If the fundamental frequency is changed, the bridge must be balanced again. If you are changing the fundamental frequency now, then at that time you have to change the LC components. You have to tune that LC components to get your fundamental frequency. Whatever the frequency you are keeping at the input terminals as a test wave, with that frequency you have to adjust. If L and C are fixed components, then this measure is suitable only to test the has a fixed frequency. So many wave analyzers are designed with fixed frequencies. Some of the wave analyzers are designing with the variable wave frequency. So fixed frequency analyzers and variable frequency analyzer. Two types of analyzers are available. So if it is fixed frequency, it cannot be find the total harmonic distortions. Okay, so if it is variable, then we can change any input of the test wave. Then we have, by using LC bridge, we have to fix that frequency values, whatever the fundamental frequencies you are given to the circuit or to the analyzer, and you have to measure the total harmonic powers by using that wave analyzer. This is the principle behind under this one. Right? Next. These indicators can thermocouples are square law VTMs, where VTMs are vacuum tube voltmeters. We have different types of voltmeters, thermocouple type voltmeters and VTVMs, vacuum tube type voltmeters. So, whatever the indicators, harmonic indicators you are connected in between the C and terminals, those can help to indicate the values. Okay, this indicates the RMS values of all harmonics. For all harmonic components, it will produce the RMS values. When a continuous adjustment of the fundamental frequency is desired, a Wien bridge arrangement is used, Wien's bridge method. So, by using Wien's bridge method, if you are changing the fundamental frequency continuously, for this type of behaviors, this fixed frequency wave analyzer we are not using. At that place, we are proposing a new method called Wien bridge method. So, by using the Wien bridge method, that is the second concept of harmonic distortion analysis is Wien bridge method. The first one, employing a resonance bridge. This is the first concept or the first type of harmonic distortion analyzer. The second type of harmonic distortion analyzer is Wien bridge method. Right? By using this Wien bridge method, we are measuring the harmonic or the distortions of the harmonics. So, this is the Wien bridge method. In this Wien bridge method, here we have a transistor first of all. Here we have a bipolar junction transistor, and here we have R3, R4 collector and emitter resistances, and base resistance we have the two biasing resistances, and next at the output of this transistor, at the collector side we have a capacitor, resistor and variable capacitor option, and here at the emitter side we have a capacitor. In between these two terminals we have connected a C2 variable capacitor and R2 resistance, and finally here we are measuring the harmonic distortions output. So, this is the analyzer based on the Wien bridge operation. Here we have an amplifier circuit. So, at the input of this amplifier circuit, we are giving the test input signal. That is the test wave input. Here we are giving for a wave analyzer. We have to give the wave input. The wave input we are giving at the amplifier input. At the output, here we have a Wien bridge method connectivity network. So, this from this connectivity network, we are getting the final harmonic distortions output. Harmonic distortions output we are measuring at this terminals here. Here we have C1, C2, where C2 is the capacitor which is connected in between C1 and emitter terminals. C1 and emitter terminals. So, you have to remember this is, you have to keep in your mind. Then we will see the theoretical explanation for this concept. Right. The bridge is balanced for the fundamental frequency. Right. At the Wien bridge also, at the starting we are keeping the bridge in the fundamental frequency. The fundamental energy is dissipated in the bridge circuit elements. So, the fundamental energy is almost completely dissipating at the bridge circuit elements. Only the harmonic components reach the output terminals. The harmonic distortion output can be measured with the help of a meter. So, whatever the harmonic power will be available, that is available at the output terminals, is only available at the output terminals, and we are measuring that output only by using a distortion meter. For balancing the bridge in the before circuit, previous circuit, in this circuit, if you want to balance the bridge, you have to take C1, C2 is equal to C, R1, R2 is equal to R, and R3 is equal to 2R4. So, see here, where R3 is this one, where R3 is equal to 2R4. So, this is the R4. If it is 1 kilo ohm, okay, then it is 2 kilo ohms. If it is 3 kilo ohms, it is 6 kilo ohms. Okay, next C1 and C2 is equal to C. C1, C2 is equal to C. So this capacitance, this one, this one, this one. Almost all we are keeping to the same value. Next, R1, R2 is equal to R. R1 and R2 is equal to R. So the normal resistance value we are keeping, a constant resistance we are keeping. So that is the bridge balanced condition for the fundamental frequency. Whenever the fundamental frequency, we are taking the values of resistance and capacitances like this. Next. So that is the Wien-Bridge method. That is the Wien-Bridge method of the harmonic distortion analyzer. Next, coming to that harmonic distortion analyzer by using bridged T-network method. So whatever the bridge network we are taking, the bridge network we have taken, but this is the style of T method. So see here, this is the T-type style. In the T-type style, the first we have LC tank circuits, LC component, LC components, and for this LC, this is the variable resistor we are connected in the parallel. Okay, so this is the total arrangement. At the input terminals in between L and C, one side of L and C terminals, we are giving the test wave input, right? One side of the L and C components, we are taking the test wave inputs. Another side of L and C components, we are taking the harmonic distorted output. Okay, in between these two capacitors, we are connected a variable resistor. So this is the bridged T network method. Okay, now coming to the explanation of bridged T network method. In this above figure, the L and C, this L and C components are tuned to the fundamental frequency. So these L and C components we are tuning for the fundamental frequency. This L and C components we are tuning the fundamental frequency, and R is adjusted to bypass fundamental frequency. R is adjusted to bypass by the fundamental frequency. So if by adjusting this R also, we can bypass the fundamental frequency. The tank circuit being tuned to the fundamental frequency, the fundamental energy will circulate in the tank and it is bypassed through the resistors. Whatever the concept just now we discussed. So whenever you want to bypass the circuit, you have to adjust the L and C components. Only harmonic components will be reach the output terminals and the distorted output can be measured by the meter. So whenever the input fundamental frequency you are giving, the fundamental frequency is tuned to this one and it is grounded. If the fundamental frequency is not came from the input signal, if the harmonics are, when the harmonics are entered into the circuit, these harmonics are reached to the harmonic distorted output. So whenever this input signal you are fixing the fundamental frequency, so in that frequency whenever the harmonic distortions are available, those will be allowed to the output terminals. Okay. Only the harmonics will be reached to the output terminals. The Q of the resonance circuit must be at least 3 to 5. Okay, so the output will be available at the output of these terminals. Okay, this is about T-type network method. Okay, next coming to that other way of T-network method. So another type of T-network method. We are keeping the previous circuit. We are keeping this complete circuit here. The bridge type T network we are keeping here, and at the output side we have output meter, and here we have an adjustable attenuator, we have an amplifier circuit, here we have the switch position, and we have the AB connectivity. See here, whenever the switch is connected to A position, what happened? Whenever the switch is connected to B position, what happened? That we will see now. So see here, if the switch is connected to A position, see what happened. The amplified information will be connected to the bridge network. The amplified information shorted directly given to the bridge T network. Here we have an adjustable attenuator is there. So you can skip this adjustable attenuator and you can give the direct information to the bridge T network. Otherwise you can give two informations to the bridge network. Okay, so that is if you short switch to A. right? If you short the switch S to B, then this is the connection. So see here, the amplified information 100% attenuated here. The attenuated information without this bridge network presence, the output is connected to the output amplifier. So see here. So when switch A connected, we skipped this adjustable attenuator. When the switch B is connected, we skipped this bridge T network. Okay, so these are the two switch positions. Let us see exactly what happens whenever these switches are connected in position A and B. The switch S is first connected to point A. First we are connecting to the point A so that the attenuator is excluded. The attenuator is excluded and the bridge T network is adjusted for full suppression of the fundamental frequency, that is minimum output. So whenever the switch is connected to A position, the bridge T network is adjusted to full suppression of the fundamental frequency. So that is connected to the fundamental frequency. At that time, we will get the minimum output parameters. Right. The minimum output indicates that the bridged T network is tuned to the fundamental frequency, and that is the fundamental frequency is fully suppressed. So whatever the fundamental frequency we are connected to the input test wave input to the amplifier, that is completely suppressed and it is not reached to the output network. Okay, there is no output available. The switch is next connected to the terminal B. If the switch is connected to B terminal, then that is the bridged T network is excluded. So now, previously the adjustable attenuator is excluded. Now we are excluding the T network, the bridged T network we are excluding. Attenuation is adjusted until the same reading obtained on the meter. So whatever the output of the attenuator will be available, the same output will be available at the output meter. The same output will be available at the output meter. So that is the information will be available when the switch is connected to the B position. The attenuator reading indicates the total RMS distortion. So whatever the attenuator output is we are getting at the output meter, that is completely in the RMS information. The distortion measurement can also be obtained by the means of a wave analyzer, knowing the amplitude and the frequency of each component. The harmonic distortion can be calculated. So whatever the information you are passing through the adjustable attenuator, this output is connected to the output amplifier, and the total harmonic power you are going to be calculated. The total harmonic power you are going to be calculated from that attenuator information. However, the distortion meters based on the fundamental suppression are simpler to design and less expensive than the wave analyzer. So whenever you are designing the circuit for the fundamental frequency suppression type, then it will be very less in cost for designing the circuit. The disadvantage of that, they give only the total distortion and not the amplitude of the individual distortion components. So in these three methods, we are getting the total harmonic distortions which will be available from that input signal component. But individual components we are not collecting from here. Right. So this is about harmonic distortion analysis. So in today harmonic distortion analysis concept. So harmonic distortion analyzer. In this harmonic analyzer, first we have seen what is the fundamental suppression type. We have seen the fundamental suppression type. So from this fundamental suppression type, we have seen three methods. So the first one, resonance bridge method or bridge resonance method. Next we have seen Wien's bridge method, and we have seen T-network bridge method, and we have seen other forms of T-network bridge method. Totally we have seen the three components. The third one, the third category is divided into two categories: normal T-network based and the last one, other T-network based method we have seen. So these are the concepts we have seen in the today's class. Okay, so this is about harmonic distortion analyzer. In the next class we will see spectrum analysis. Okay, thank you.